Welcome to this lecture of computational hydraulics. We are in module 4 surface water hydraulics, and this is unit number 8, unsteady 2D surface flow, and this is the last unit of our module 4. Learning objective of this particular unit: at the end of this unit, students will be able to solve 2D unsteady shallow water flow using explicit approach. Problem statement: let us consider one river and irrigation command system. Let us say that this is my river system and this is one rectangular 2D area, which is the command area, and we have some hydraulic structure on the upstream side. So, water is supplied from that hydraulic structure for irrigation purpose, or the problems with severe flooding situation, where due to upstream release from dams or barrages, there will be inundation in the downstream areas. So, we can conceptualize the problem as 1D and 2D case. Individually we can solve these systems. So, in our previous lecture class, I have already discussed 1D channel flow or unsteady channel flow case. So, now let us consider the case for 2D surface or free surface flow. We are talking about free surface flow because top portion of the of our water flow situation that is exposed to the atmosphere. Now, in this case, let us consider our main core structure. In this one, our hydraulic system is 2D, or that is our mathematical conceptualization. So, we need to write 2D governing equations. 2D problem is unsteady in nature in this case, because time evolution of surface flooding or surface water movement we can track using those governing equations. So, we will have one governing equation, initial condition and boundary conditions. So, in this case we need to discretize our domain either with structured or unstructured mesh, or with structured or unstructured point generation. So, let us consider the case where we have utilized finite volume method. Now, using for using this finite volume method with rectangular coordinate system or with uniform gridding, we need to consider structured mesh. So, numerical discretization, that is in terms of finite volume, and algebraic form, the resulting equations will be nonlinear in nature. So, what we can do, we can simply reduce the problem to a pseudo linear or pseudo nonlinear problem, and we can solve it using explicit approach. Obviously, in explicit approach the technique is straightforward, we do not require any iterative method, only iteration or time stepping is required for forward marching. and finally, we can get the solution for the problem. So, in this case, conservative form of the governing equation, depth averaged mass and momentum conservation equations for surface water flow can be written like this, where u is vector, E is vector, G and S all are column vectors. Individually, if we see these components, this is H, HU, HV, HU, this is HU square, G H square by 2 HUV, and this one G HV, HUV, HV square, GH square. Now, in this case on the right hand side we have minus QS, that means something is there which is going out of the system. We can consider infiltration as minus QS from the bottom of our ground surface. Now, in this case, first row that represents our continuity equation, and second and third row, these two are considering momentum equation in x and y directions. We are not considering any variation in z direction. Obviously, if we want to consider the variation in z direction, you have to consider the full scale Navier-Stokes equation, but this is depth integrated equation, that is why we are not considering the variation within our system. So, non-conservative form can be written from conservative equation like this. In this case, obviously del f by del u, this term is again vector. If we consider one dimensional case, this is like Jacobian, but in this case this Jacobian part is again vector. If I write this H as U1, U2 as UH, U3 as VH. So, in this case I can write the first vector as U1, U2, U3. Now, E is nothing but E2, U2, this is U2 square by U1. This was U square and this is U2 square, means this is square divided by our H. So, obviously, this is U square H. So, like that I have converted all the terms for this E and G in terms of U1, U2 and U3. Obviously, UVH, this term will be U1, U2, U3 divided by U1. So, after converting this, we can get the information about this del f by del u. So, obviously, Jacobian can be calculated like this. Here f is again vector. In this case, this is E I plus G J. Now, for this one we can individually calculate del u by del E by del u and del G by del U components. So, we can get this Jacobian matrix out of this. So, how to calculate this one? This is essentially E 1, this is E 2, this is E 3, this one is G 1, this is G 2, this is G 3. Now, for del E by del U, E and U both are vectors. In this case, we will have del E by del U 1, del E 1 by del U 2, del E 1 by del U 3, del E 2 by del U 2 U 1, del E by del U 2, del E 2 by del U 3, and last one, which is which is our del E 3, del E 1, del E 3, del U 2, del E 3, del U 3. Now, in this case directly this can be calculated like this. Now, what is del E by del E 1 by del U 1? There is no del U 1 here. So, obviously, this is 0. Del E 1 with respect to U 2, obviously, this is 1. Again, we do not have any U 3. So, 0. Like that, we can calculate individual components for this Jacobian matrix for individual E and G components. Now, after this calculation, we can discretize our domain, because we need to use finite volume method. So, obviously, for finite volume method, we need to divide our domain into number of cells. So, let us say that on x direction I have total m number of cells, on y direction I have n number of cells, and like our classical problem, we have this gamma n, which is Neumann boundary, gamma d, which is specified boundary. There can be situations where my domain is totally closed one. In that case, I can consider all sides here, all sides, this red. So, all sides I have closed boundary or 0 Neumann kind of condition, but obviously, we need to see individual components in that case. So, starting with the discretization of the governing equation. So, as per a finite volume method, the governing equation is integrated over element volume in space. So, what is that element volume? This omega p. Now, in this omega p, if I integrate starting from t to t plus delta t, that means nth time level to n plus 1 time level. Obviously, we can write this with this integral sign. Now, in this case I have changed this divergence of f and utilized it directly here. So, divergence of f, this will give individual components. So, this will be nothing but if I take del, this is del by del x, del by del x I plus del by del y j, and if I take divergence of that, so obviously I will get del E by del x plus del G by del y. So, after that I can start the discretization of my temporal term. So, temporal term is nothing but in this case del u by del t directly, and this is similar to the discretization that we have utilized for our groundwater equations. So, for central cell, which is the pth cell, we can write this, and u p l plus 1 minus u p l, and L represents our time level in this case. Again in this case I can write this for central cell P. This should be divergence of f. Divergence of f can be written like this. Again this f dot n f, n f means f represents a particular phase, divergence of f in that one and a f there. So, for all phases for a rectangular domain we have east, west, north, south. For all domains we can write these components. So, we will have 4 components out of this, the east, west, north, south. This is similar to our previous discretization. Now, the difference is now we can calculate the flux values at the interface. Now, for that calculation we need to consider flux at right face or right side, flux from left side, and u r is the value on the right side, u l is the value on the from the left side. So, with these values we can discretize our full flux terms, because in groundwater equations we have discretized the derivatives directly, but in this case we need to find out the flux values at the interface. That is why this part is important. So, in this case we can write this from the information from the right side, left side, this u l which is nothing but u p up plus del up, and right it is E minus del E. So, if I see this notation, this is nothing but this utilizes the mean mod notation that we have discussed in our equations for conservation law, and up and ue these values are at the cell centers on the east cell, west cell, and uee this is for our east to east, that means extreme east cell which is adjacent to east cell. Now, for this one we need to see one thing. What is that? That is our mean mod calculation. As per our mean mod calculations, we have this a value. If modulus of a is less than our modulus of b, and a b both greater than 0, and if it is b modulus a and a b greater than 0, then it is b, otherwise it is 0 in this case. So, if I utilize this concept for discretization, I can obviously we have up and p minus uw, these are a and b values. If modulus of a is greater less than modulus of b and a b greater than 0, then it is a. If modulus of b is less than modulus of a b greater than 0, this is b, otherwise this is 0. So, if I apply it directly in this case, what I will get, this left side up plus half of this one, this is delta p. In first case, if modulus of a is less than modulus of b, obviously this is up plus half up minus ue minus up, because we have the first condition. So, for first condition, this is up plus ue divided by 2. Now, if I have second condition, that means if I have b there, then what will be the situation? If I have b there, then this is up plus half up minus uw. So, that means this is 3 by 2 up minus half uw. So, what is this? Physically it means that if this is my interface east, this is pth cell and this is cell w, whatever information is coming is from left side. This is my left side, this is my right side. Initially, when we have a value, we have seen that this quantity is P and E, these two values with average at the interface. But if it is B, then we will have this value, which is nothing but this value at interface. So, this is nothing but the interpolation or linear interpolation of u w, this is u w, this is u p, and this is u from left side, although it is u e, but we are calculating u l e. Similarly, if I see the thing for right side, the right side again, if the first quantity, this is A, this is B, and first one is my E minus half U E minus U P. So, obviously, in this case it will be U E plus U P divided by U E plus U P divided by 2. From right side again, if it is second quantity is U E minus half U E E minus U E. So, this is again 3 by 2 3 by 2 U E and minus half U E E. So, again the information that is coming from my right side, this is P, this is W, this is E, and this is east to east cell. So, for this cell, if the information is there, so I can take again linear interpolated value using this E E and E here. So, from right side we are getting linearly interpolated value at the face or right side value. Like that, we can have 4 combinations, 2 for the case of left side, 2 for right side. Now, similarly, when we will be calculating the value of west face, so this is our P cell, this is west, this is W W, and this is east one. So, we are considering this W face. In case of W, again we need to consider left and right one, and in that case we have A and B. And the first one, if this is half U P minus U W, then this is half of U P plus U W, but if it is U E minus U P, U E minus U P, or this is del P in this case. So, del P is coming here on the right hand side, is just opposite. For left hand calculation, it will be UW. So, either it should be average of P and W, or the information should flow from other side. It considers WW. So, obviously, from this side it will be WW. For north face, this is again similar. We have top and bottom cell, this is P, this is south, this is north, and we are talking about this particular north face. So, for north face we need to consider NN, that means north cell, and UP, UN, UP, US and UNN. So, this is the structure there, and we can calculate this UBN and UTN. Similarly, if we have component on this side, so that means this is south face, we have P, this is north, this is south, and you can have SS or south cell there. So, with this we can again calculate the flux values at the interface. So, for all phases we can calculate this. Now, this is our general Mead-Mon limiter definition. Alpha value, which is the coefficient, can be calculated as per the suggestion of Nozick 1995. So, alpha should be greater than equal to maximum value of lambda p. Lambda p can be calculated from Jacobian matrix, and it is the largest eigenvalue. Obviously, this can be approximated with lambda p equals to V p plus root over H p. V p is the resultant velocity, and H p, this is our depth of flow in case of surface flooding or surface water flow. So, we can utilize predictor corrector approach for explicit case. So, obviously, in this situation, if we need to calculate the flux value at east face, west, north face, so that is nothing but on east side it will be E, west side it will be W, north side it will be G, south side it will be S. So, individually these components will be there for calculation, and S value is evaluated at lth or present time step, and this U star, which is calculated predicted step or intermediate step in this case, and in corrector step U star star value is calculated, and U star value in this case again we have this one. So, in simplified form again E, W, G, N, these values can be calculated there. At future time level or L plus 1 in our case, which is the T plus delta T level, we can simply add these values and take average of that. Actual variables now can be calculated after this step. So, what is that actual variable? Actual variable is for pth cell u p 1 is the actual variable, but u p 2 is not the actual variable. We need to divide it by p 1, again v p we need to divide it by u p 1. So, after this corrector step calculation, we need to update this. So, in our predictor corrector step, for both the cases we can use the same del E or del P these values, because that will lead to numerical stability of the scheme in this case. Now, we need to provide or specify boundary no flow boundary condition. We know that if we have no flow boundary from all sides, obviously UHE, UHW, VHN, VHW, these VHS, these quantities will be 0 individually, and if we want to implement this with our governing equation, then let us see. For east boundary, obviously at east boundary we will have this component, this flux component we need to calculate at east boundary. What will be the value? For this case, only this component will be there. So, at east boundary u is 0, which is normal to this boundary. So, this term is 0, this term is 0, this term is 0. Obviously, E will be 0 half g h square and 0, and g again this will be having this can be calculated for north and south boundaries. So, there will be no change in this case. Similarly, for west boundary, again this quantities will be 0. So, approximately to calculate the east phase value, we can specify half g p square, which is the cell center value there, but this is approximate specification of boundary condition. We need proper characteristic curve or method of characteristics to specify the boundary condition for explicit case. Not boundary, obviously in not boundary case V is 0. So, this quantities are 0. So, G will be 0 0 half G h square for no flow case. Now, in case of our south boundary, this is again not boundary. If I have a south boundary on this side, this is north, we can have a south boundary here, and for south boundary the thing is same, this G s, this quantity will be 0 for some components for no flow case. This next to east boundary, we need to implement our governing equations there. Next to west boundary, next to north boundary, next to south boundary, again we need to implement it, and northeast corner. So, obviously, in this case for north corner this will be having 0 components, east corner this will be having 0 components. So, northwest, then southeast and southwest corners, we can have similar situations. So, for our surface water flow, a specification of boundary condition and more or less the solution, it is difficult due to nonlinearity present in the equation. So, what we can do for basin flooding or simplified modeling case, we can reduce our shallow water equations and we can drop some terms like acceleration terms, and we can solve that equation for simple flooding situations. So, this is our usual shallow water equation. I have written it in terms of this Qx, Qy. Qx, Qy is nothing but this is UH and VH. Now, SF and SY, these quantities we can directly write here. Now, what we can do? We can drop some of the terms, and we can get the reduced form of the equation. So, what is that? That is, we can retain our continuity equation, and we can drop other terms in our momentum equations by neglecting acceleration terms like this. Now, if I combine this Sy and Sx, these are related to water surface slopes, and water surface slopes, if I equate it with energy slope, then I can write this simple equation there. And finally, by combining discharge and continuity equations, final form of inertia equation can be written like this, and you can see that this has got similarity with our groundwater flow equations. It is near to, or it is more or less equivalent to that equation. If I simplify with this consideration that alpha h, which is function of h only, and 0 inertia equation can be further simplified like this. I can transfer this term h term on the right hand side. Obviously, this has got only one variable for 0 inertia model. Usual surface water flow equations, we need to solve h u v, but with a 0 inertia case we can reduce our problem to one variable case and we can solve that problem. So, again if I apply our finite volume method here, I can directly write this integration or integrated form of the equation, and we can discretize that for solution of different kinds of problems. But obviously, in this case the movement or acceleration terms we are neglecting. Obviously, in that particular case we have to consider slow movement of water. So, slow flooding or irrigation application of water through canal system can be considered as one kind of example of the for this particular equation. This is my irrigation system, and for this irrigation system I can supply water from the canals So, the movement of water from this canals will be slower. So, I can model this using this simplified version of our shallow water equation or 2D surface flooding equation as a zero inertia model. So, after flooding, obviously the water will move from one cell to another cell, and there will be flooding situation in the total area if water is applied through this canal outlets. So, this kind of problem can be solved with zero inertia model, and we can directly apply our numerical approach for solution of that. So, this is all about our 2D surface water hydraulics with unsteady turn. This is the flooding situation in a typical canal system. So, obviously, there will be slow movement of water, and this can be modeled using a zero inertia case. Thank you. ওখানে কিছুটা বাদ দিতে হবে।